Now we're going to look at the second of the two types of sequences that we'll study, that is geometric sequences. Okay, obviously we need to recognize and know how to write what a geometric sequence. We'll look at finding the sums of both finite and infinite geometric sequences, and we will of course model and solve problems. So a geometric sequence is defined similar to the way the arithmetic sequence is, in that it's a series of numbers. But the relationship between the numbers in a geometric sequence is such that there's a common ratio. So in other words, if I have a sequence, oops, A1, A2, A3, A4, and so on, then we're going to look at the ratio of A2 to A1, and it's going to be the same as the ratio of A3 to A2. In other words, A2 divided by A1 is the same as A3 divided by A2, and so on throughout the series. So I could look at it as a ratio of A2 to A1, or I could say that I need to multiply A1 by some number to get A2, and I'm going to multiply A2 by that same number to get A3, and so on all the way up the series. That number that we're multiplying by, or the quotient of this division, is known as the common ratio. Okay? So the question is, are these sequences geometric? If so, what's the common ratio? Well, here, okay, it's 2 to the n is the definition. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So this is indeed a geometric sequence, and the common ratio, called r, is equal to 2. Okay? Here, we're multiplying by 3 to the n. Okay? 3 to the nth power. So this is our first term. We're going to multiply by 3 to the first. And there we go. Okay, if I multiply 12 by 3 to the second, I'm going to get 108. And I could start at the initial point and move out, or I could just say, you know what, to get from 12 to 36, I multiply by 3. To get from 36 to 108, guess what? I multiply by 3. To get from 108 to 324, guess what I multiply by? Okay, so this again is a geometric sequence, and the common ratio is 3. Looking at this, you could figure out, just you're probably getting used to the syntax now, I've got some number raised to the power n, where n is the term number. Okay? Well, if I take that, that is going to be my common ratio. So if I to move from negative 1/3 to 1/9, I multiply by negative 1/3, and so on. Negative 1/3, negative 1/3. Okay, so this is again a geometric sequence, and its common ratio is equal to negative 1/3. Okay, so here's the definition. A sub n, the nth term of a geometric sequence, is equal to the first term times that common ratio raised to the n minus 1 power. And if you think about why it's n minus 1, if here's a geometric sequence, a1, a2, a3, a4. Now we're going to rewrite all of these subsequent terms in terms of a1, the first term. Okay, so a1 is of course just a1. To get to a2, I need to multiply a1 by the common ratio. So a2 is the same as a1 times r. Okay, and so on. I could do that. Okay, a3 is going to be a2 times r, but a2 is this, so I have to multiply a1 r times r, which gives us a1 r squared. Okay? So you could see that the third term, the exponent of that r, is 1 less than the term number, and that is where this n minus 1 comes from. Right, so what are the first 5 terms of the geometric sequence? Okay, so we know that a1 is equal to 3, and r is equal to 2. So going by our definition of the geometric sequence, a sub n equals a1 times r to the n minus 1. Okay? Knowing that, we could plug in what we know. Okay, we're solving 1an. Okay, we know A1 is 3. We know R is 2 to the n minus 1. So let's get the first 5 terms. A1 is equal to plain old 3. We know that. It's given in the problem right there. Okay. A2 is going to be 3 times 2 to the n minus 1, which is 1. 2 minus 1 is 1, equals 6. Okay. A sub 3 is going to be 3 times 2 to the second, or 12. A sub 4, 3 times 2 to the third, or 24. And A sub 5 is going to be 3 times 2 to the fourth, which is 3 times 16, or 48. So here are the first 5 terms of our geometric sequence. Notice that to go, we know our common ratio is 2, so to go from 3 to 6, I multiply by 2. 6 to 12, multiply by 2. Multiply by 2. Multiply by 2. Okay? Okay, so the 15th term of a geometric sequence whose first term is 20 and common ratio is 1.05. So let's just document what we got. We know, we know that A1 is unknown at this point, right? Or do we know it here? No, I'm sorry. First term is 20. Okay. We want to know A sub 15, and the common ratio is 1.05. So let's go ahead and plug this in. We know that A sub 15 is going to be equal to A sub 1 times R to the n minus 1, which is going to be 15 minus 1. That's equal to 20 times 1.05 to the 14th power. And that is approximately equal to 39.599. Okay. 12th term of the geometric sequence. Right? So A sub 1 equals 5. Our common ratio here, we can just look at the sequence. 15 divided by 5 is 3, or 45 divided by 15 is 3, so the common ratio is 3. Okay, so A sub 12 is going to equal A sub 1 R to the n minus 1, which is going to be A sub 1 is 5, R is 3, and the n minus 1 is going to be the 11th power, because we're interested in the 12th term. And this comes out to be 885,735. These things get pretty big pretty quickly. Okay, so now we're going to look at what it takes to add up the sum of a finite geometric sequence. And the formula is right here. If you have a sum from 1 to n, so the first n terms of a sequence, it's going to be the sum of each of the terms. And that simplifies to this. This is the formula you need to remember. So let's give it a try. Okay. The sum of the first 12 elements of this sequence, 4 times 0.03 to the n. So the sum of the first 12 is going to be equal to 4 times 0.3 is 0.12, times, so this is A1, 4 times 0.3 to the first power, times 1 minus R, R is 0.3, to the n is going to be 12, divided by 1 minus 0.3. Just following the formula. And this will come out to be 5.714 if you did it all out. You can figure out each of the terms and add them up. This should save you some time though. Okay. Now, that was the formula for a finite series, or sequence rather. Um, if the common ratio is less than 1, the series diverges, so we can actually take the sum of an infinite number of elements of a series. And if R is less than 1, if we take this formula, what happens is this becomes some fraction R. Let's say R is a half. And if we raise a half to a power, what happens? Well, that's equal to 1/4. If we take 1/2 to the third, that's equal to 1/8. And what's happening as this power gets bigger, this number is getting smaller. Okay, so as this number approaches infinity, okay, 1/2 to the infinity power is going to approximately be equal to 0. It's going to get really, really, really tiny. So what happens is that this term can be just eliminated because it's essentially becoming 0. When n gets really big, that goes away. So we have a1 times 1 over 1 minus r, or a1 over 1 minus r. It's actually a simpler formula for figuring out the sum of an infinite series for geometric. Of course, the common ratio, the absolute value of the common ratio, has to be less than 1. It has to be a fraction in order for that to work. Okay, so let's take a look at this sum. Okay, for part A, our sum is going to be equal to 4, which is our first term, divided by 1 minus our common ratio. Okay, so in other words, a1 here is equal to 4, and the ratio is equal to 0.6. Okay, this equals 4 over 0.4, or 10. Okay, so the sum of the infinite series, okay, that is indicated here, if you add up all the numbers, you're going to come up with 10. Exactly 10. Okay, let's document again here. A1 is equal to 3. And what is our common ratio? Well, what do I have to multiply 3 by to get 0.3? 0.1. Okay. So plugging into our formula, our sum is going to be equal to a sub 1, 3, first term, divided by 1 minus the common ratio, 1 minus 0.1. That's going to be 3 over 0.9. And that comes out to be approximately equal to 3 1/8.